Welcome to multivar calculus, weeks 1 and 2. So here we're looking at Stewart's Calculus 9th edition, chapter 12 summary. This is a non-comprehensive list of concepts and examples from the chapter. So I do recommend that you go through chapter, and there may be a few concepts that I don't cover here that are covered in the textbook. So you may want to look more in detail inside the textbook for additional explanations or additional problems. So the first thing that we talk about in multivar is vector operations. There are always algebraic and geometric properties of vectors that we need to consider. So here's a few things you need to know. You need to know how to compute and interpret geometrically any of the concepts that we encounter, such as placing 2 points in a plane into component form, placing a vector in what's called IJK form, standard basis form. So that's in 2D and 3D. Okay, usually in this class we'll deal with 3D figures, but also you should be very familiar with the Cartesian plane, the R2 plane, which is a normal XY plane that you deal with. Operations that you can do to vectors: add, subtract, dot product, cross product of two vectors. You can do combinations thereof to any of the vectors. How to find a unit vector: that's just essentially taking the vector v and dividing by the length of the vectors. That's how you get a unit vector. And here's an application to the said slide is force and resultant force as a vector representation. So in this next example, see one such example, how to use force. So here we can see a constant force F moves an object along the line segment from 102 to 538. Find the work done if the distance is measured in meters and the force done is in newtons. Okay, so what you want to do is realize that the work is the force times the distance, which in our context, if you translate that to vector form, that's work is equal to force vector dot product with the distance vector. The force vector, obviously, we have is just in standard basis form, so we could just place this like this: 3, 5, 10, and dot question mark. We need to find what this vector d is, and we can do that by simply taking the 2 points that are given and then subtracting them. So you have 5 minus 1, the first coordinates, 3 minus 0 in the second coordinate, and 8 minus 2 in the third coordinate. So let's see, we get 4, 3, 6. So we'd have to take the dot product of these. Remember, the dot product is always going to be some kind of scalar that comes out of here, or if you have some irrational numbers in here, that could also happen over here on the right, rational or irrational. But we take the dot product, so let's do that. 3 times 4 plus 5 times 3 plus 10 times 6, that's the dot product. So you get 12 plus 15 plus 60. So we have 87. joules. So we usually write joules because that's the standard measurement for work when the force is given in newtons and the distance d is measured in meters. So that's an example of how you would apply, let's say, the dot product and component form of a vector in this context. So you have 87 joules. All right, so we have more properties. So properties of the dot product: if f dot v is 0, then uv are orthogonal. That's important because orthogonal means perpendicular, so that could be 2D or 3D vectors. If you take their dot product and it's 0, then the two vectors are orthogonal, meaning they meet at 90-degree angle. We want to be able to compute 2 by 2 and 3 by 3 determinants. This will become important as we move through and talk about normal vectors, among other things. Property of cross products. If UV lie in the same plane, then the cross product is orthogonal to the plane. So how you compute the cross product is by using determinants. So we had to take the determinant of, if it's a 3 by 3, then we do a 3 vector, 3 tuple vector. Then we would have to take a 3 by 3 matrix and take the determinant of that matrix, and then we would see that if the UV lie in the same plane, that this cross product is orthogonal to that plane. So orthogonality, again, becoming important. We'll see why this is important in just a minute. We want to be able to find the angle between two vectors. This is described in your book. We want to be able to compute projections and components and know what that means geometrically. This is also described in your textbook. Geometric interpretation of length and of the cross product U cross V as the area of parallelogram. So if you do have a 2D, that's a 2 by 2, two tuples here, okay, the cross product gives you the area. And if it's a 3 tuple, then we get that we get the volume of a parallel pipe by computing scalar triple product, which is a combination of cross product and dot product, and taking the length of that. So that's called the scalar triple product, and that will give you the volume of a parallel pipe, essentially a parallelogram, a three-dimensional parallelogram. Here's an application to the cross product: torque, computing torque. Torque is orthogonal to the position vector and to the force vector. So this is the orthogonality of the torque is usually talked about using the right-hand rule. So well, we can go on to the next example and see how that applies. So example 2, find the magnitude of torque about P if 50 Newton force is applied to the figure. So here we have 50 Newton force applied from 30 degrees here. Here's the position vector, if you will. It's 40 centimeters. And you're applying this force to the tip of this. What's the torque? Okay, so that's the question here. So let's go through the solution. So the solution is actually not too bad. So we have the torque is going to be equal to the length of the position vector, we'll call that R, times the length of the force vector, which is called that F, and then it's going to be sine of theta. And what that theta is the angle made between the force vector and the position vector. So if we go to our diagram, the angle between the position vector, which here is 40, and the force vector is going to be this theta in here, which is complementary to 30 degrees. So we know that's 60 degrees in here. So the torque then is 40, because that's the length of the position vector, times 50, that's the force vector, sine of 60 degrees. So the torque is going to be 2,000 times the sine of 60. Torque is 2,000 times rad 3 over 2, which is 1,000 radical 3. And we can use a calculator to estimate that if you wish, 1,000 times radical 3. And then if we want, this would be Newton centimeters. Now, usually it's Newton meters. You can convert that to Newton meters by making this 0.4 and calculating it this way. So you'd get that this is 10 rad 3 Newton meters, which is typically what torque is measured in. It's measured in Newton meters, but since this example didn't really specify either one, would be fine. So that's a torque. So with the right hand rule, okay, you would take your right hand, you'd point your index finger in the direction of 50 newtons, and your middle finger in the direction of the 50 newtons, your index finger in the direction of the position vector, okay? Then your thumb should be pointing down into the page, okay? So this would be 10 root 3 Newton meters into the page, and that's the direction of the torque vector. The torque is actually orthogonal to the position and force vectors, okay? So that's a property of the torque vector. So that's just an example of how we use torque. Here's another example. Find values of x such that these vectors are orthogonal. Well, we want to take the dot product of the vectors because we know that when you have the dot product of, let's say, any 3 tuple def, if that's 0, then they are orthogonal. So let's take the dot product here. And let's see what we get. We get 6x plus 8 plus x squared equals 0. Again, I'm just taking the dot product. So we have a trinomial, which we can factor x plus 4, x plus 2. And we see that x equals negative 4 or x equals negative 2. So if x is one of those two, then these two vectors are orthogonal because the dot product is 0, which means they meet at a right angle. There are also other types of vectors, of course, such as parallel vectors. You have perpendicular vectors, which this is, and you can have vectors that just intersect. So yeah, there are all these three types, which you should be familiar with. There are more examples in the textbook regarding all three of these. Um, of course, if I went through everything, it would be a much longer video. So I'm just trying to do a summary. Here's another points, equations of lines and planes. So you could have parametric equations, direction numbers. What that is basically the slope, more or less in a 3D form, and symmetric equations, which is just another way of writing parametric equations. You want to be able to parameterize a line segment. Now, this part doesn't seem like that important at this moment, and in fact, it won't really come into too much play at the very beginning of this course, this parameterizing a line segment, but it comes into play more in the later part of the course where we start talking about integration. The normal vector equation of a plane, scalar equation of a plane, these are things you can see in your textbook. Two planes are parallel if their normal vectors are parallel. So that's when the cross product of the normal vectors is 0. That's how you can tell if the two planes are parallel. Find the angle between two planes. This is similar to the angle between two vectors, has to do with computing the normal vectors for the planes, and then using a formula, which is again found in your book with the cosine formula, and finding a distance from a point or a plane to a plane. This is also found in your book, this formula. So there are lots of formulas that I'm just referring to here that are in your textbook. Be sure to just look at all these different formulas and know how to use them. Let's look at a couple of examples, and then so first example, find the parametric equations for this line. This line goes through 1, 0, negative 1, and is parallel to this line. Let's tackle that first. And we'll tackle number 2 in a second.